So, hello. So, Parimala will continue our second lecture today.
Hello everyone. Can you all hear me? It's fine. Yeah. Okay. So I feel totally nervous person to go ahead because somewhere if I mention V infinity, just just correct me. So I just start exactly where Hanke left. Maybe I'll just repeat a couple of lines what he said. So invariants for quadratic forms. So as we already saw, the essentially three invariants were defined by. Okay, so the dimension of a quadratic form is simply the dimension of the underlying vector space where the quadratic form lives. Once again, let me remind you, the quadratic forms I am looking at are non-degenerate or regular throughout. The dimension invariant is just the dimension of the underlying vector space. And somehow we would like to define invariants at the level of width groups, not at the level of quadratic forms. So the hyperbolic space has even dimension. So let's define dim2 of Q to be the dimension of V mod 2. So this is the very first invariant for quadratic forms. So this defines a homomorphism from width group of K to Z mod 2Z, sending a class of Q to the dimension mod 2. In fact, clearly this is a surjective homomorphism, and IK, the fundamental ideal, is the kernel of, let me call it E0 to continue with the sequence later on. So I0, the kernel of E0 is simply the fundamental ideal of the quadratic form Q. Now the second invariant is simply the discriminant of Q, which is, as mentioned in the earlier talk of Hanke, it is just the determinant of the representing matrix. And we saw that you can, for different choices of basis, the associated matrices correspond under orthogonal equivalence. So this defines a well-defined element in K star mod K star squared. But once again, as I said earlier, we would like to define the invariance on bit classes, not just on quadratic forms. So for instance, with this definition, if you take 1 minus 1, the discriminant will be minus 1, which may not be a square in K star mod K star squared. So in order to do this correction, I'll just define the discriminant as, I'll attach a sign to it, it's called the sign discriminant, is simply minus 1 power the dimension n into n minus 1 by 2 into determinant of AQ. The correction of sign factor is simply to kill the discriminant of hyperbolic forms. So once you fix the dimension of a quadratic form, and when you look at invariance, it's enough to take the determinant because this sign is fixed. This is the second invariant for quadratic forms. And the next invariant is, once again, it was already mentioned in the Hanke's talk or even in Conway's talk, so-called Clifford invariant. Of Q. So we have given the quadratic form Q, we have the Clifford algebra of Q associated to Q. This is simply the tensor algebra of the underlying vector space mod out by the ideal generated by V tensor V minus Q of V. Okay, this is simply the Clifford algebra. In some sense, we have all seen Clifford algebra through the universal property. Essentially, this is universal for the property that algebras which contain the vector space V with V squared equal to QV, then there is a K algebra homomorphism from the Clifford algebra to the given algebra. So universal for the property that V squared is QV among algebras containing V. So this is the Clifford algebra, and the tensor algebra has a positive gradation. So, and V tensor V is even grade and QV is a scalar. So CQ comes with Z mod 2 grade C0 of Q plus C1 of Q, as C0 is just putting all images of all the even grade elements, and C1Q set of all odd grade elements. So there is a gradation on CQ, and so I'd like to record this, that if dimension Q is even, then C of Q is a central simple algebra over K. What is the central simple algebra over K? It is simply an algebra over K, which is a form for the matrix algebra. When you tensor the algebra over the algebraic closure, it becomes some n by n matrices. This could be a definition for central simple algebra. And if dimension Q is odd, then C0 of Q is a central simple algebra over K. And these central simple algebras live in the Brouwer group of K, which is defined somewhat analogous to the Witt group, except we are building up a group structure on isomorphism or sort of equivalence classes of central simple algebras. You just take isomorphism classes of central simple algebras over K, mod out by now the so-called Brouwer equivalence. Brouwer precisely introduced this group to study the totality of central simple algebras over the given field. Brouwer equivalence is simply A Brouwer equivalent to B if and only if after tensoring with the matrix algebra they become isomorphic. Some matrix algebras, mm of A is isomorphic to mm of B for integers nm. Okay, so two algebras are equivalent if up to matrix factors they are the same. So we know the structure of such algebras through Wedderburn theorem and so on. And let me denote by the two torsion of the Brouwer group of K. This is the notation for me. This is the two torsion in the Brouwer group of K. Those elements, okay, I didn't say what is the, of course the zero element is the class of the matrix algebra, and the negative of a class of A is simply the class of the opposite algebra. Okay, you have a very natural isomorphism of A tensored with its opposite with mn squared of K, where n squared is dimension of A over K, or more naturally there is an isomorphism of A tensor A out through left and right multiplications with endomorphisms of A as a vector space over K. So the negative of the algebra is just the opposite algebra. So the two torsion denotes the two torsion elements in the Brouwer group of K. So these algebras classes, the representatives come equipped with an involution, and I want to say that if dimension Q is even, in any case the Clifford algebra always has a very canonical natural involution. So there is an involution on the Clifford algebra, so you have this vector space supporting the quadratic form sitting inside the Clifford algebra, inside the C1 part, grade 1 elements. So there is an involution tau from CQ to CQ, which has the property that tau on the generating element, tau B is B. So if you take V1 tensor V2 tensor Vn as chain in tensor algebra, the involution reverses the chain. So you have such an involution. So it is, Clifford algebra is always isomorphic to its opposite algebra. So we have therefore, if dimension Q is even, then the class of C of Q is an element in the two torsion of the Brouwer group of K. And if dimension Q is odd, then the even Clifford algebra of Q, this is an element which is in the two torsion of the Brouwer group of K. So given a quadratic form, we always end up with associating to it an element in the two torsion of the Brouwer group. We simply define C of Q to be the class of C of Q or the class of C0 of Q in the two torsion of the Brouwer group of K, depending on dimension of Q even and dimension of Q odd. So this gives the next invariant for quadratic forms with values in the two torsion of the Brouwer group of K. Okay, so now So let me just go back to the discriminant. So the discriminant actually gives a homomorphism from the filtration, the fundamental ideal of K to K star mod K star squared, namely the discriminant which we just defined. This is a homomorphism which again is clearly surjective, and the kernel of the homomorphism is precisely discriminant is the square of the fundamental ideal. This is a very easy exercise to do. Namely, the discriminant homomorphism is surjective onto the group of square classes, and the kernel of the discriminant is precisely the next level of the filtration on the weight group, namely I squared. This is easy to check. And now the Clifford invariant actually gives a homomorphism C from the next level of the filtration, I squared of the fundamental ideal to the two torsion of the Brouwer group of K. The next invariant, it is defined, note that the discriminant as well as Clifford invariant, they are all defined on all quadratic forms, but the discriminant induces a homomorphism at the level of Ik, and the Clifford invariant induces a homomorphism at the level of I squared K. Okay, then of course, in the previous cases we have seen the maps are surjective, and we knew what the kernel of the maps were for E0 and E1. So the next natural question is the map C surjective, and what is the kernel? Of course, one can guess. We want the kernel to be I3 of K, the third power of the fundamental ideal. Okay, these were sort of questions pending for a long time in the 60s and 70s. So let me just describe the image of the twofold Pfister form, a generator for I2 of K, 1B. If you take this twofold Pfister form, C sends it to the class of the algebra I defined in the last class, the generalized quaternion algebra associated to a pair of elements in the field, pair of non-zero elements. This H minus A minus B is the dimension 4 algebra, the quaternion algebra, with relations IJ. This is with a pair of generators and relations Ij is minus Ji. Okay, this is the central simple algebra of dimension 4 over K, and this twofold Pfister form is mapped under the Clifford invariant to the class of this quaternion algebra. Okay, so we know that I2 of K is generated by twofold Pfister forms. We saw it in the last class. So this is generated by such twofold Pfister forms. If we expect this Clifford invariant map to be surjective, it would mean that the two torsion of the Brouwer group of K would be generated by the classes of quaternion algebras. For me, the quaternion algebra definition is with respect to a pair of elements in K star. So this was indeed the long-standing question, whether the two torsion whether the two torsion of the Brouwer group is generated by quaternion algebras. And in fact, the theorem of Mercurial, this answered this question, long-standing question in the affirmative. And in fact, this is also the very first case, non-trivial case of solution of Milnor conjecture, which I will come to immediately, namely for degree 2. So Mercurial's theorem says that C is surjective. That means every element in the two torsion of the Brouwer group is in fact generated by quaternion algebra, is class of a tensor product of quaternion algebras. That's the content of this. C is surjective, and further the kernel of C is the next level of the filtration, I3 of K. So in fact, this could be thought of as giving a presentation for the two torsion of the Brouwer group of K. So the three invariants, dimension, discriminant and Clifford invariant, these are so-called classical invariants for quadratic forms. Maybe it will be not very complete if I just don't talk of signatures at this point. Maybe I'll quickly mention what is the signature invariant for quadratic forms. We already saw in the morning what is signature of a quadratic form over the field of real numbers. Okay, so you would diagonalize a quadratic form and count the number of plus ones and number of minus ones and take the difference. We saw it twice. So this is the or we saw it thrice. So the signature is just defined if you have a form over the real numbers. So, but one can also define for any field. Suppose K is any field, we can talk of the space of orderings of K. Okay, the space, ordering of K is something like, I will not go into the detailed definitions, it's like giving the so-called set of positive elements with whatever properties you expect for positive elements. Okay, essentially, if you take for instance a number field, each embedding into the real numbers gives an ordering for the number field. It gives definition of positive elements. So this is the space of orderings, and given a quadratic form Q over K and given an ordering omega in omega K, the space of orderings. So if you diagonalize the form A1, A2, AN, so with respect to this ordering, you can see whether AIs are positive or negative. Okay, so you have declared certain elements are positive and the complementary set of elements as negative. Of course, 0 is in the intersection and the only element in the intersection. So you can determine whether, just look at how many positive elements are there in the diagonalization and how many negative elements are there in the diagonalization, and just you can define the signature of Q of this quadratic form with respect to this specific ordering as simply number of AIs positive at omega minus number of AIs negative at omega. Okay, we just define it in the same way we define the usual signature. In fact, this defines the homomorphism from bit group of K to, you can just talk of functions from the space of orderings with values in Z. So take an ordering, a quadratic form defines its signature which is its element in Z. This could be thought of as functions from the space of orderings to integers. Okay, and if these are not random functions, they are they have more properties. In fact, one can equip the space of orderings with a certain topology, so-called Harrison topology and so on, with respect to which these are in fact continuous functions. Okay, this is called the total signature homomorphism. Of course, if you just take number field, which is the case most familiar to us, then this omega K consists of the finite set of real places of K or -1 places of K, and this just gives a finite set of integers giving the signature at the real completions. Okay, so these are, including signature, these are the so-called classical invariants for quadratic forms. So if you take a finite field here, then in fact the dimension and discriminant form a complete set of invariants for quadratic forms over a finite field. You take two quadratic forms, they have the same dimension and the same discriminant, then they are isomorphic. Then if you pass from Fp to p-adic field Qp, let me assume P not 2 for simplicity, okay, so here dimension, discriminant and C, the Clifford invariant, these form a complete set of invariants. Once again, given two quadratic forms, if they have the same dimension, the same discriminant and the same Clifford invariant, then the quadratic forms are isomorphic. Okay, there's a complete classification in terms of these invariants. Of course, you can pass from Qp to Q or any number field. Here, of course, if the number field has ordering, certainly you have to take count of signatures. So we have a complete set of invariants once again, dimension, discriminant, the Clifford invariant and the total signature. Okay, these form a complete set of invariants to determine the isomorphism class of a quadratic form. However, if you go to a slightly more complicated field, by that I mean, for instance, if you take QPT or something like that, you take function fields, go pass on to function fields and so on, one knows that these invariants are not sufficient to classify quadratic forms. You need higher invariants, and this was the program which was stated in Milner's paper, the so-called Milner conjecture in the 70s. So he proposes higher invariants, and he wants to know what is the range for the higher invariants and what are the relations. Okay, this is the content of Milner conjecture. To define the higher invariants, we should know where they live. Okay, the dimension lives in Z mod 2Z, the discriminant lives in K star mod K star squared, and the Clifford invariant of quadratic form lives in the two torsion of the Brouwer group of K. So you see a pattern in the range for these invariants. So these are precisely part of so-called Galois cohomology groups. Let me quickly go over the definition. So gamma K is the absolute Galois group of the separable closure of K over K. Of course, this is a profinite group. So this is an inverse limit of the finite Galois extension. L over extension is L over K. L is contained in K bar. L over K finite Galois. Okay, this inverse limit gives it a profinite topology, and M is a discrete gamma K module. By that we mean M is a module over this profinite group gamma K, which is continuous for the profinite topology on gamma K and the discrete topology on M. Okay, so that is what we mean by a discrete gamma K module. Then we can define this Galois cohomology groups Hn gamma K M. This is simply this becomes a direct limit of the Galois cohomology of the finite Galois extensions Galois L over K with values when M invariant under the Galois group of L. You take the M is a gamma K module, take the elements fixed under gamma L, and then that becomes a module over G L over K, the quotient group, and then you just take the usual finite cohomology groups and run it over the direct limit as the L runs over finite Galois extensions as before. This is the nth Galois cohomology of the absolute Galois group of K with values in M. Basically, any element you can just track down to the cohomology of some finite Galois extension. Okay, it just consists of various species living in at finite levels. So essentially the only group we'll be using in describing the invariance for quadratic forms is when M is mu2. That is, in the case we are assuming the ground field has characteristic different from 2. So this is the square roots of unity, which is plus or minus 1, and the Galois action on this is trivial because plus or minus 1 belongs to the base field K. This is a trivial gamma module, so sometimes this is also denoted by Z mod 2Z. So the module plus or minus 1 under the Galois action will just denote by Z mod 2Z, the Galois module, and we'll have this abbreviation Hn of K simply stands for Hn of gamma K with values in this particular coefficients, Z mod 2Z or mu2. So this is the definition of the Galois. These are the groups where the invariants are going to take values n. Okay, so we see immediately that H0 K is simply Z mod 2Z, the invariance. And what is H1 of K? So we have this exact sequence of Galois modules, mu2 to K bar star to K bar star. This is the squaring map, x goes to x squared, and the kernel is simply mu2. So this is an exact sequence of gamma modules. Whenever you have an exact sequence of gamma modules, there is also an exact sequence in Galois cohomology. After all, it is built up of finite pieces where we know there is a long exact sequence. So when you write the corresponding sequence, invariance here is K star, is as K star, and the invariance here is K star to H1 K mu2. And the next term, H1 K with values in K bar star. H1, I'll put the Galois group at this point, gamma K K bar star. This is trivial. This is one of the very first computations one makes with respect to Galois cohomology. This is the Hilbert 90. This H1 is 0. So H1 K mu2, this is just the squaring map. So H1 is simply K star mod K star square, the square classes. So if you take an element A, a square class, this denotes an element, this within brackets will denote the element in H1 mu2 corresponding to this connecting map in Galois cohomology. Okay, this is the first Galois cohomology group. And if you look at the same sequence and go on with further down, you see that H2, the basic fact is H2 of gamma K with values in K bar star is simply the full Brouwer group of K. So this is again a the cohomological description of the Brouwer group of K. If you fit it in here, you see that the two torsion of the Brouwer group of K is nothing but H2 of K. H2 gamma of K with values in mu2 is simply the two torsion of the Brouwer group of K. Now we see that the dimension discriminant and the Clifford invariant live in these Galois cohomology groups of degree 0, 1 and 2 of the absolute Galois group with coefficients in Z mod 2Z. So the next invariants were defined with values in the higher Galois cohomology groups. But the basic difference is, while the three invariants we mentioned before are defined on classes of all quadratic forms, the higher invariants are defined only at particular levels when the previous invariants vanish. Okay? They are not invariants defined on the totality of quadratic forms. Possibly that's why they are not called classical invariants, because they are not defined on all the forms. Okay, the next invariant E3 already was defined by Arison in his paper in 75, H3 of K. This invariant is called Arison invariant because he showed that there is some invariant on I3 which has the property that if you take a I3K, we know is generated by threefold Pfister forms. This maps under E3 to minus A, cup minus B, cup minus C. Note that when we write within brackets, this stands for the elements in H1 defined by the corresponding square classes. And the cup product you take, because we are taking Z mod 2 coefficients, it lands in Z mod 2. So this gives an element in H3 of K, Z mod 2Z. So Arison proved that such an invariant Arison, he showed that E3 is well defined on I3. In other words, if you make the specification of that on the threefold Pfister form, it takes this particular value. He showed that this extends, because after all I3K is generated by threefold Pfister forms, and he showed that it extends to homomorphism. It respects relations in I3 and it defines a homomorphism from I3 of K to H3 of K. And then now maybe I can state Milnor conjecture. So okay, the assignment En from n-fold Pfister forms K to Hn of K given by 1A1 tensor 1A2 tensor 1AN mapping to minus A1 cup minus A2 cup minus AN. So first of all, this a priori you take a element in P and K. There are several ways in which you can write it as a n-fold Pfister form 1A1 10. There is no uniqueness for these AIs. So if you send it to this, the first question is this map well defined? Okay, that is part of the conjecture. Is well defined. That is the first part. Then leads to homomorphism. That is the second part. Homomorphism from In of K, which has these as generators, to Hn of K. This is the first part of the conjecture. Further, En is surjective as in the previous cases, and kernel of En is In plus 1 of K. So this is the full content of Milnor conjecture. So there are invariants for quadratic forms defined at the level of In with values in Hn of K, and this assignment leads to a surjective homomorphism of Hn of K, Ink to Hnk, and the kernel of Ens is precisely the next level of filtration. So this is the content of Milnor conjecture. This was in the 70s, 72 I think, a paper of Milnor. And in fact, several cases of Milnor conjecture were known, and in fact the case of number fields and so on goes back to a paper of Tate in the 70s. So one knew that Milnor conjecture holds for nice fields like number fields and so on. So this also gives in some sense some kind of generators for the nth Galois cohomology. When you look at this, so the P and K elements map onto such cup products. The conjecture asserts that the nth Galois cohomology is generated by such cup products. This is one of the contents of Milnor conjecture. Of course, now, as I mentioned, E2, the case n equal to 2 is the first non-trivial case of Milnor conjecture for a general field, which it's due to Mercury. Now, Milnor conjecture is a theorem. Conjecture was proved by. So I am just stating the quadratic form aspect of Milnor conjecture. There is also a k-theoretic aspect. So this was settled by Vygotsky. And then in this paper of Vygotsky, Orlov and Vishik, they complete the argument for the case of quadratic forms. It is not instant from the k-theoretic case. It just has to go through some more working outs. So now this is a theorem, so we can take Milnor conjecture as a theorem now, which is very nice because after all it says that there is a complete classification of quadratic forms in terms of Galois cohomological invariance. So what does it mean? Suppose you take two quadratic forms Q1, Q2 over K, and suppose dimension is the same, and suppose the discriminants are the same, and the Clifford invariants are the same. Then we cannot say E3s are the same because E3 is not defined unless the previous invariants vanish. So when you take the difference between these two forms, then the previous invariants vanish because of these conditions. You assume that all the successive invariants are 0 for the difference between the two forms, then for all n, then it gives that Q1 is actually isomorphic to Q2. So in fact, if you assume dim2 equal to dim2, then you will get that the classes are the same in the width group. If you assume literally they have the same dimension, then it says that the two forms are isomorphic. So, however, this condition looks that you have to check too many invariants matching, but that's not the case. If you are given two forms of a given dimension, then in fact you need to go up to only certain finite n to check the difference has trivial invariance. This is because of the following theorem of Arison-Pfister. So they prove the following very basic result, that if Q, the class of Q is in the nth level of the filtration of the width group, and suppose Q is anisotropic, take any anisotropic form in In of K, then the dimension cannot be too small, it is at least 2 power n. If you take anisotropic forms defining classes in the nth level of the filtration, then the dimension of the form has to be at least 2 power n. So if you take two given forms of certain dimension n, say, this difference has a specific dimension 2n. So it cannot belong to Im for a very large m. So we just need to go up to at most suppose dimension of is n, something 2 power something, which is not too large, because this will be, if it belongs to something bigger than 2 power n, it will vanish. Okay. Even 2 power n is too large, but you need to go only up to a finite level to check the invariants vanish. Okay, so we'll come back to this later in one of our applications. So now, how much time I have? Half an hour? How much? 20 minutes? 20 minutes, yeah. Thanks. So maybe I'll start with Pfister's theory of multiplicative forms. Okay, this is the, I want to spend a little bit of time explaining some of the intricate theorems of Pfister, leading to also some of the solutions of some questions on quadratic forms. So we already called certain kind of forms as Pfister forms, right? So a form like 1a1, you take tensor product, n-fold tensor product of binary forms like this. This we called something isomorphic to this was called an n-fold Pfister form. So what is the speciality of these forms? The speciality is that, so when you take the non-zero values represented by such a Pfister form, okay, you take the values represented by them and look at the non-zero values represented by this form, then Pfister's theory says that non-zero values form a group under multiplication. It is a subgroup of K star. Okay, that is, for such forms, if you take two values, then the product is also a value of this form. So in some sense, they are called multiplicative forms. Not only that, what Pfister did was to characterize all multiplicative forms. So you can ask, what are all the quadratic forms with the property that the value, non-zero values form a group? Okay, it is multiplicative with respect to product for values. Of course, if the form represents, if the form is isotropic, okay, so what are the values for such a form? So if it is isotropic, it contains the plane 1 minus 1. So the hyperbolic plane represents all elements. So if once the form is isotropic, it represents all non-zero elements of the field, including 0. Such forms are called universal. So it's not so interesting to look at this property of multiplicativity if the form is isotropic. So they are going to always represent all elements. So therefore, essentially, okay, maybe I'll just state Pfister's theorem. So that let me make a definition. An anisotropic form for K, quadratic form, is called multiplicative if the non-zero values, form a group not only over K but hereditarily over all extensions of K. For every field extension L of K, the values of the non-zero values of Q over L form a group. So in some sense, hereditarily the values always form a group, then you call it a multiplicative form. Okay, and Pfister's basic result is that every multiplicative form is isomorphic to one such form. Every anisotropic multiplicative form is in fact isomorphic to a tensor product like this. Okay, we will see what are all the nice consequences. I mean, now I can't think of any proof in quadratic forms without appealing to some aspect of Pfister's theory. So maybe I'll just indicate, because I don't know, this is so beautiful algebra, that I'd like to just at least indicate what are all the things which go into the proof of characterizing multiplicative forms. Okay. Well, of course, I'll not prove the following two results which are basic towards the proof of multiplicative, the characterization of multiplicative forms. One is the Cassels-Pfister representation theorem. Cassels-Pfister representation theorem. Which says the following. So if you take Q is a quadratic form over K, and fx is a polynomial in the rational function field in one variable over K. Sorry, fx is a polynomial in one variable over K. And suppose Q represents f, the polynomial fx, over the rational function field K of x. Suppose this fx is a value of Q over the rational function field, then Q represents fx over the polynomial ring K bracket x. That means there exists GIs in polynomials such that summation AI GI squared is equal to fx. If it is representable over the rational function field, in fact it is representable over the polynomial ring. So this we will see how this is. This enables one to have specialization arguments, because if you are given polynomials, it is easier to specialize on values. So this is fundamental for specializations. And the next basic theorem I want to assume is the subform theorem of Pfister. Already we see how function fields enter into the picture in a very fundamental way. Suppose Q is anisotropic over K. You take an anisotropic form over K, and phi is any form over K, B1, B2, Bm, any form over K. Then if Q represents the form, the homogeneous polynomial associated to phi, that means if it represents b1 x1 squared plus b2 x2 squared dot 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 plus bm xm squared, that is the corresponding homogeneous polynomial associated to phi. Suppose Q represents this polynomial over where the rational function, wherever this element lives, the rational function field in n variables over m variables over k, then phi is a subform of Q. You can embed phi as a subform of Q. That means Q can be written as B1, B2, Bm, C1, C2, Cl. Okay, you can make phi part of Q, provided Q represents this this polynomial associated to phi over the corresponding function field. Okay, this is the subform theorem, which again we'll see how we can effectively use it. So let me just I just said the Cassels-Pfister representation theorem is pretty useful in specialization arguments. So if you take a polynomial p x1, x2, xn in the rational function field in n variables, and Q is a quadratic form over K, and suppose Q represents P of x1, x2, xn, this rational function over the rational function field in n variables. Suppose P is the value of Q over this big function field, then if P of lambda 1, lambda 2, lambda n, if it makes sense, where lambda i's are in K. Suppose you take a vector lambda 1, lambda 2, lambda n and specialize this rational function. Suppose this makes sense, okay, then Q represents P of lambda 1, lambda 2, lambda n over K. Okay, so this is a very useful fact that specializations of values are again values of the quadratic form. So it's not hard to see how the proof could go, because you will break it up into just say polynomial in n-1 variables with the last one as a parameter, and then just successively use Cassels-Pfister representation theorem. So first deduction is you can as well assume by multiplying by a square factor that this is a polynomial, and just successively you keep substituting using the representation theorem of Cassels-Pfister. So you get this specialization theorem. Okay, so now I'll state Pfister's theorem. So Q over K is anisotropic. Then Q is multiplicative if and only if Q is isomorphic to 1a1 tensor 1a2 tensor 1an, okay, for some n, and n is determined by the dimension of Q. In fact, the anisotropic multiplicative forms are all in dimension 2 power n for some n, and they have to be isomorphic to this such a tensor product. In fact, Pfister called these forms multiplicative forms, and eventually they came to be called the Pfister forms, because I reversed the order of history. I mean, so this. Okay, so So how much? Maybe 5 minutes. Maybe I could stop here and continue with some indication of the proof of Fister next time and go on with some applications. Thank you.